Hello everyone. Hello, my name is Ashutosh and welcome back to NPTEL's FOCT Fiber Optic Communication Technology live discussion. This course is being taught by Professor Deepa Venkitesh, IIT Madras, and I am the teaching assistant for this course, Ashutosh. Today we'll be looking over the questions on week 7. But before we go there, let us go through some of the topics that have been covered here. So on week 7, we covered about photodiodes because before this week we had already covered about the transmitters and the channels. So prior to this week, we had covered transmitter and channel. That leaves us with photodiode, that is the receivers. In photodiode, we studied the responsivity, what is the quantum efficiency. Responsivity was the amount of current that is being generated when a certain amount of power is incident on the photodiode. Quantum efficiency, on the other hand, gives us an effective efficiency count because all the electrons that fall on all the light that falls on the photodiode does not generate an electron hole pair. After that, we looked at different kinds of photodiodes, specifically silicon photodiode, which is used for the ranges in visible light, that is around 300 to 1000 nanometers, and then we looked at InGaAs, which has a responsivity which is sensitive to wavelengths of around 900 to 1700 1800 nanometer. This depends on the band gap of the semiconductor itself. Then we looked at some of the properties such as the detector rise time, bandwidth, and they were completely characterized by bandwidth responsivity trade-off. Like if you want a higher bandwidth, you would want to pull the electrons out of the photodiode as quickly as possible, but that would increase the noise in the system. And then there was responsivity of the photodiode. Now then we looked at p-n junction diode, and the photons are actually being absorbed in the depletion region itself. So when photodiode, which is positive, negative, which is an intrinsic, is sandwiched in between, this intrinsic region is used to effectively increase the amount of area available. So if this is your p-n junction diode, your pin diode would be something like P, and this is the intrinsic region where all the photons can come and get absorbed there. And then we looked at another kind of diode, which is an avalanche photodiode. An avalanche photodiode was normal P and I, and then this is highly doped multiplication region, and this is N. And after that, we looked at some of the detection schemes, such as the direct detection, which just detects the intensity. Then we looked at noise in photodiodes and the different operating regimes. Some of the noise that are available in the photodiodes are thermal noise, short noise, and dark current. We also slightly considered the amplifier noise, but it will be dealt more in the coming weeks where we go into the fiber amplifiers. And then we looked at NEP, noise equivalent power. This is also called NEP, the data sheet. And then we inverse of NEP was detectivity. Then we looked at the coherent detection scheme and the improvement that it offers in the SNR and the coherent gain. Explanation of these concepts in a important week may be a little difficult, but don't leave this week for the last moment, because it is important and questions in the exam might come from this week, because this gives you a complete idea of TX, channel, and RX, and most of the noise in the systems is in the RX itself. We assume the lasers are perfect, so most of the bandwidth limitation, rise time limitation is on the detector side, so it is very important to understand what is happening on the detector side itself. Now these are some of the formulas that will be useful while solving your assignments. This is the photon current generated, and this is the input power. So the relation between input power and photon current is given by responsivity. In this we have represented by ND. Eta is the quantum efficiency, and this relation relates the quantum efficiency with the responsivity. Now responsivity is also related to material absorption, which is here given by alpha, and W is the width. So we had discussed that if W is the width of this thing, what is the efficiency, because larger the W, more photons can be captured there. Then we looked at the RC time constant, then rise time. Then we looked at so this is just for a PIN photodiode or PN junction, whereas this is for an APD, where you see there's a multiplicative region here as well. So there is responsivity and there is input power which is present here and here, but there is also this M factor. Then there were different sources of noise. We have looked at the thermal noise and short noise. Now SNR, in this case, we are like similar to the lectures, we are only considering the average of everything. So average of current by average of current noise, which is given by RdPn square by short noise. And sorry, this should have been thermal noise, because it is the sum of this and this. And then there were two regimes that were considered. One is thermal noise limited regime, where the SNR is given by this. Short noise limited regime, where the SNR is given by this. Essentially what we have done is that in thermal regime the short noise has been ignored, and in the short noise regime the thermal noise has been ignored. Now we will move on to the some of the other formulas that are there is NEP, which is the noise equivalent power. Now NEP is the signal power divided by noise power, and when NEP is equal to 1, that means your noise and signal have the same amount of power. Similarly, we had seen the other detectivity is the inverse of NEP. Now we saw the SNR of photodiodes in the last case. SNR of APDs, we have multiplicative factor here and a multiplicative factor here in this case. You see in the thermal 4 kBT is the thermal short noise, and the multiplication factor of the APD does not come in this. It only amplifies the short noise. So that is why you will see that the M square factor is here, whereas that M square factor is missing here. So it's not that the entire, if it were present in both the cases, like if this also had an M factor, then M square factor, then this, and both of them would have gotten cancelled. But an APD is highly reverse biased, which increases the short noise, but it does not increase the thermal noise in our case. Now, one thing to note here, what I wanted to illustrate by adding it here, is that photodiodes are squared of electric field detectors. Like if you have two electric fields, let me see if I can add another page. The important point to consider here is that, let's say I have a photodiode here like this, and some light is falling on it of energy electric field E1, and some other light is falling on it of energy E2. Now the current output which is given in this case, the current output is RD times E sig plus ELO. This has specifically been done in the case of homodiene heterodyne detector, but it is important to understand that the current output, which is given by I itself, is RD. It's not EI. So let me put it this way: if EI is the electric field falling on this, what is I1, which is EI square, and I2 is E2 square. The point I wanted to add by ensuring that the photodiode is a electric squared of the electric field detector and not an intensity detector is the point that if IFT is not equal to RD times I1 plus I2, this is not correct. I of t is equal to RD E1 plus E2 whole square, and usually E1 and E2 are complex numbers. This is just something to keep in mind, that the photodiodes do not directly sum the intensity, they sum the electric fields. This is only possible if we assume that if we have same polarization. Now moving on to this, I have some examples of what a because all of us are eventually going to design this in real life. So I just wanted to look at some of the data sheets that are available there. So let's go to Thorlab spin photodiode. Seems to be a trouble in my hyperlink. So if we go to a Thorlab's photodiode, we could just pick any one. So you see there are these with silicon, there are these with silicon. Let's look at one and we'll take a look at its spec sheet. Now you see this is what a normal photodiode looks like. The output power is given by responsivity into the falling power with the RL in here. Now it also tells you the region of wavelength that is, because this is a silicon photodiode. It works from around 200 to 1100 nanometer and its peak responsivity is around 730 nanometer. They give you the effective area, rise time, fall time depending on the load that you put. In this case they have given a 50 ohm load and you have reverse biased your photodiode by 10 volts. Now there is also some amount of dark current that is present in these photodiodes inherently, and that they are saying is typically 0.3, but the maximum they have set the limit of 1 nanoamps. All of these photodiodes, as ma'am have suggested, it can be modeled as lumped elements of R, L and C, and this is telling that at 10 volts reverse bias the typical capacitance is 6 picofarad. Photodiodes is usually reverse biased and it tells you that maximum reverse voltage is 25 volts, and they have also given a typical circuit of how to connect your photodiode, where this is your PD and this is your bias circuit with the noise removal thing. And this is for this particular photodiode, this is the graph. Now this graph, as ma'am had already illustrated, changes from manufacturer to manufacturer because they have slightly different manufacturing techniques, and that alters the band gap a little bit. Now similarly we have a Thorlab's APD data sheet, which can be seen. This is what a APD looks like, and we'll look at APD 210. This is also a silicon APD, but we can look at the spec sheet here in this case. And you can see that the spectral response given by this graph here goes from 400 to 1000 nanometer, and the maximum incident power for these APD is 10 milliwatts. 10 milliwatts is just 10 dBm, and similarly this gives you a mechanical outline as well. So reading these data sheets are important because it will give you factors such as NEP. NEP you can see here calculated as 0.4 picowatts per root hertz, and this is 2 picowatts per root hertz. All of these are AC coupled with an output impedance of 50 ohm. Signal output is 1 volt, and connector output is BNC. BNC is a usual RF connector that can go up to 2 gigahertz. And this is how you take a look at the data sheet and see what is the NEP. So parameters that are important in a data sheet are, before you decide a photodiode, you should know what wavelength you want to operate at. You want to know the wavelength, you want to know the responsivity of your. Now wavelength will either decide if you use silicon photodiode or engaged photodiode. After that wavelength, you will look at responsivity, and depending on that you will build a transimpedance amplifier. Transimpedance amplifier, because it is easier for us to measure voltage than current. And the second part is, after building a TIA, you are able to increase the bandwidth. gives you gain, which would eventually not have been possible just via resistors. So usual model that we have studied is you have a photodiode here like this, and then you put a resistance across, and then you measure this voltage. Now the problem in this is that if the photodiode current output is very small, if you have 1 microamps falling on 1 microwatt falling on it, let's say the incident power is 1 microwatt, that goes through a 1 kilo ohm resistance. Now 1 microwatt going through a 1 kilo ohm resistance, assuming a responsivity of 1 amperes per watt, the output current is responsivity into power, which is 1 amps per watt into 1 microwatt, which is 1 microamps. Now what is the voltage drop across this resistance? R, which is 1 kilo ohm. V is equal to IR. So 1 microamp into 1 kilo ohm. This is 10 raised to the power -6. This is 10 raised to the power 3 is equal to 10 raised to the power -3 is equal to 1 millivolt. Now this is a low number. So to get rid of this problem, we build circuits what are called TIA circuits. We build what are called TIA. Transimpedance amplifiers. And in transimpedance amplifiers, you have it like this, and then there's a feedback. This is just a circuit to illustrate the point. And whatever is your feedback here, and then you have another resistance here. You have another resistance here, and in this case, your V out. If the gain of this TIA is G, let's say G, we can easily make it as 100K. So now the V out will be G instead of this case where we had simply V is equal to IR, our gain. If it is 100, let's make it a reasonable number of 100. Kilovolts per amp. Now in this case, if this is your gain, then your V out would be G into I. I was the current that was generated, so this is 100 kilovolts per amp into 1 microamp. So this is 10 raised to the power 2 into 10 raised to the power 3 volts per amp into 10 raised to the power -6, which is 0.1 volt. Now this is a much more reasonable number that we can measure. But while building this, we have to be sure that the gain is not absurdly high. It is within the gain bandwidth product of the amplifier used in our case. Now we will look at some of the assignment questions. In this question, in order for coherent receiver to its fullest benefit, the power of the LO is the local oscillator, should be high such that the short noise generated by LO is much greater than the thermal noise. If you remember the curve that was like this, and one was here. So this was the thermal region, and we want to operate in this region where short noise is the dominant feature. So the question is, what is the LO power required for LO induced short noise to be at least 10 times the thermal noise at room temperature? Assume load resistance of 50 ohm and responsivity of 1 amps per watt. Now responsivity of 1 amps per watt is a reasonable number. Now let us write down everything that has been given to us in the question. So we have been given it should at least be 10 times the thermal noise. So short noise should at least be 10 times of thermal noise, and we would want our power local oscillator to be much greater than the power of the signal itself. What else is given? My load resistance is given as 50 ohm. My responsivity is given as 1 amps per watt. And do we need something else? Let's see. Let us write down the formulas that we know. Now, the short noise variance that we would like to calculate, you can go and take a look at the formulas in the earlier sheet, and you can see that the short noise is 2q I plus I del f. And if I assume the dark current to be 0, sigma short noise would be is given by 2q I del f, where del f is the bandwidth and id I have assumed to be 0, whereas my sigma square thermal will be given by 2q. Let us go before we look at the thermal noise. So, or let's write the formula for thermal is the formula for thermal noise. You can see, go back. Formula for the 4 kBt Fn del f by RL. So formula for currently 4 kBt del f by RL. In this case, because this is a normal photodiode, the Fn will be 1. Now, it has been given that if you look at the question again, we want the LO short noise to be at least 10 times the thermal noise at room temperature. So, let us find the short noise. So, our task is, now we have to find (2q) IP del f. Now I don't actually know what IP is, but I know IP is given by my responsivity times load resistance times, oh, this is just current, so there is no load resistance in this case, responsivity times power of LO times del f. Now from the gravity relation we have sigma s square. We want this condition to be satisfied, which is 2q RD into power of local oscillator into del frequency is 10 and thermal was 4 kBt delta f by load resistance, where kb is Boltzmann constant. Now if you put all the numbers here, let's see how if we can simplify that. This del f goes away, this 2 becomes 5. So what we are interested in finding is the power of the local oscillator, which will be given 5 times 4 is 20 kBt divided by RDQ RL. Let's just copy this over to the next page and we'll try putting reasonable numbers. Let's see. We know this is 20 and kb is the Boltzmann constant, which is 1.38 into 10 raised to the power minus 23. Temperature in this case is in Kelvin. So this is 273 plus 25, which is 298 Kelvin. 298 divided by responsivity has been given as 1 amps per watt into charge of the electron into 50 ohm. Let me just pull up my calculator and see what are the numbers. Into 50, which comes out around 10.27 milliwatts. Where the value of E that I have used is the electric field, which is given by 1.60 into 10 to the power minus 19 coulombs. Now this is given in milliwatts, but we have learned from our experiences that handling power is easier in the dB scale, because losses and gains just become addition and subtraction in the logarithmic scale. So PLO in dBm would be 10 log 10 by 1 milliwatt, and this is also milliwatt. Now this should be log of 10.27 is 10 into 1.011. So this is equal to 10.1 dBm. So that answers the first question, is what is the LO power required for the LO induced short noise to be greater than 10 times the thermal noise at room temperature. That is why we use 273 plus 25, which is 298 Kelvin, and assuming the load resistance of 50 ohm and responsivity of 1 amps per watt. Now let us look at the second question. Second question is, consider a coherent homodyne receiver with 13 dBm PLL logged oscillator and direct detection receiver. And so we have two schemes here in this case, where they have a homodyne scheme. Even if the homodyne scheme was not mentioned here, we would know that it is a phase logged local oscillator, and phase logged means that I am disciplining my slave laser with what is the frequency or the phase of my master laser, and that is the locking. And if the lasers are locked, let's say by injection CD, the frequencies are disciplined as well. That would mean that this is a homodyne detection. So here we have a two scheme, which is a homodyne detection and a direct detection. Both receivers use pin photodiodes with similar responsibility, 0.75 amps per watt, and negligible dark current at room temperature. So ID is equal to 0. The detectors are designed to operate at 1550 nanometer, and the electrical bandwidth is 40 gigahertz for both the cases, and load resistance is 50 ohm. Now 50 ohm is a number that keeps popping up, is because there are two impedance standards. One is 50 ohm and the other is 1 mega ohm. 1 mega ohm is 10 to the power 6 mega ohms, 10 to the power 6 ohms. These two standards keep coming up because 50 ohm is where the maximum power transfer happens in an RF line. Now find the input signal that is required to achieve an electrical SNR of 20 dB for direct detection receiver and coherent receiver. So we want, let us write down everything that we know first. And although not mentioned here, we have to use a power of local oscillator as 13 dBm. So let us do that. No, it is mentioned here, 13 dBm. Now I know that 10 dBm in the last case we calculated is around 10 milliwatts. So 13 dBm is just twice of the 10 milliwatts. So this is 20 milliwatts. We have to consider a responsivity of 0.75 amps per watt, load resistance of 50 ohm, delta F is 40 gigahertz, and we are again in the temperature of 298 Kelvin. I don't think we need anything else. Now the first question is, we want 20 dB SNR for direct detection receiver and coherent receiver. So let us look at that. First, let us look at the thermal noise variance. Because thermal noise variance would be similar in both the cases, which is lambda t square, which is given by 4 kBT del F by RL. So substitute the values, 1 into. We had 40 gigahertz, so 40 into 10 raised to 9 divided by 50. Let me dot my hand calculator again, and we have. So in all these calculators, all of these values are already pre-stored. Like Boltzmann constant is, if I remember correctly, it is stored at 25. Yes, it is stored at 25. 4 kb 298 into 40 gigahertz divided by 50, which gives me a number 1.32 into 10 raised to the minus 11 square. Now let's calculate short noise for direct detection. Let's call this sigma short noise direct detection, and this is given by 2 into charge of the electron RD PS del F. Now we do not actually know what PS is at this point, so let's just call this 2 into 1.6 into 10 to the minus 19 into 0.75 into 40 gigahertz into PS. This turns out to be 9.6 into 10 raised to the minus 9 PS amp square. Now similarly, let us calculate the short noise for homodyne scheme. So it is similarly again 2Q RD, but instead of signal we have power of local oscillator here and del F, and this time we know the power of the local oscillator, so we do times with the charge of the electron into same responsivity. Power of the oscillator was 20 milliwatts into 40 gigahertz. Let me put that in real quick. Which is so we see that already we can see that the short noise for local oscillator is vastly superior compared to the short noise of the not the local, the short noise of the homodyne detection is lower than the short noise of the direct detection scheme detector. Now we have been given the task that the SNR should be 100. Now the way we can find SNR, so the final objective is not to decrease or increase the absolute unit of power itself, but to boost up the SNR. So we see, let's calculate SNR for direct detection scheme. SNR for direct detection scheme, which is given by RD square P signal square divided by direct detection scheme short noise plus thermal short noise. Remember, the thermal short noise remains the same in both the cases. So if I substitute the numbers here and if I trust my calculations from the notebook, let me just do it again. Direct detection scheme is 9.6 10 raised to the power minus 9. This is 1.32 into 10 raised to the minus 11. Similarly, we can calculate this for we can calculate SNR HOMO, which will be given by for RD square PS LO, because remember in the exponential term this was PS this 2 was outside if I remember correctly, PS, PLO. So the square of this is how we get this term, and then you have sigma S homo plus sigma thermal. Now we want a SNR of 20. And the question, if you'll go and revisit the question, it is given SNR of 20 dB. This is electrical SNR of 20 dB. Now SNR of 20 dB means a factor of 100, because from dB scale we go to 10 log P by P, like P by P ref. So a 20 dB gain would mean 20 is equal to 10 log P by P ref, and this is log base 10, so this becomes 10 raised to the 2 P by P ref, or P is equal to 100 P ref. Now this P ref could be our SNR in this case, so this would contribute to my SNR in linear scale is 100 is equal to 20 in dB scale. So now I just need to find out 100 is equal to 4 into 0.75 whole square into PS into local oscillator I know as 20 milliwatts, and then divided by 1.92 into 10 raised to the power minus 10, the short noise of the homodyne, and the thermal, which is same for both of them. When you solve all of this, your signal power should come to 0.45 microwatts, which is almost minus 33.4 dBm. We have calculated the SNR for HOMO and we assumed it to be 100, but let's, for the sake of completion, also calculate the SNR of the direct detection scheme. Which is given by, hold on, I think I had done almost this. Oh yeah, so let's just do a comparison here, and let's say I want 20 dB SNR here as well. So this becomes, what is 0.75 whole square? This is 0.5625 PS square by 9.6 EPS plus 1.32 into 10 to the minus 11. Now when you solve this, your PS would come out as 0.049 milliwatts, and when you put it in log scale, this is 10 log 0.049 divided by 1 milliwatts. Milliwatt goes away, and this becomes 10 log 0.049, which is minus 13.09 dBm. So you see the case, in the case of direct detection scheme for SNR of 100, I need minus 13, almost minus 13 dBm of power, whereas in the case of homodyne receiver, I need a minus 33.4 dBm of power. So I need considerably lower amount of power at the receiver to generate the same signal to noise ratio. Now let's look at the fifth question. The fifth question is, find the input power signal PS level for which the coherent detection provides better SNR compared to the bit. We have already seen that for same SNR, which was 20 dB or 100 in linear scale, and the given parameters. Homodyne is better, but there are cases where direct detection scheme is also helpful, and it depends on the power level, because the amplification application is being provided by the LO on the local oscillator. So we would want to see the case where SNR homodyne is equal to SNR direct detection scheme. Now this would be my SNR for RD square PSPLO 2Q RD PS plus PLO, because short noise is dependent on both the powers, plus 2RD PS PLO delta F is equal to RDPS by 2Q delta F. And when you solve all of this, this is equal when PS is equal to PLO. That means for equal PS is equal to PLO, we have a similar SNR, and therefore for equal SNR in both the cases, PLO is equal to P signal. That means if my local oscillators are the same power as my signal, there is no improvement in the homodyne detection scheme, which is given here. That would mean it provides a benefit whenever my signal is stronger than this, so, or my signal is lower than 13 dBm. So this would mean benefit is